Good morning, students. In the previous class, we were discussing the high frequency modeling of the transistor, and we had also seen the Miller effect capacitance, which means if there is a capacitance in between input and output, then how to have its counterpart both at the input side and the output side so that we can easily perform our mathematical analysis. So, based on that discussion, we will continue today's class now. You can see here that the transistor's amplifier circuitry is modeled along with other parasitic capacitances. Here, especially CWI, CBE, CBC, CCE, and CW0. They are parasitic capacitances. And we had modeled the high frequency circuit using RC network. Now you can see all the series capacitances as well as the shunt capacitances which were external, they are not shown in this model at all, because when these blocking capacitances are at the input at a very high frequency, x equals 1 over 2 pi fc, so f is very high, that x is very less, so we have shorted it here. Similarly, the output capacitance which was there here at the collector, that is also shorted. Similarly, the emitter capacitance which was there, it was also called as bypass capacitance, that was shorted. That's all fine as far as high frequency is concerned. Now, at the input we have a wire, and wire is always two wires together, because with reference to ground there is one signal wire. When they are together, even in the wire, when these two wires are separated by means of a insulating plastic material, even that wire will have its own capacitance with respect to ground. That is how the CWI is shown here. Now, why CWI is shown here is, in case of low frequency, it was not considered at that time, because the value of this capacitance was very less. It is actually very less. It is in terms of picofarad or femtofarad or even attofarad. It is either 10 power minus 12 or 10 power minus 15 or 10 power minus 18. That way the capacitance of the wire is very less in the low frequency domain. But in the high frequency domain, as you know, x equals 1 over 2 pi fc. When f is very high, even this xc can become predominant. That is why we have written this CWI here. Similarly, at the output side, you have the output wire. The same thing is applicable. Output is connected by means of a wire, and that wire also will have a capacitance, that is parasitic capacitance, that is shown here as CW0 with reference to ground. Now, in the low frequency analysis, we had ignored the base to emitter junction capacitance or the base to collector junction capacitance or even the collector to emitter parasitic capacitance. But in the high frequency analysis, we cannot ignore, as once again I should say, x equals 1 over 2 pi fc. When f is very high, x is very low. So, we have to show this base to collector junction capacitance. In fact, base to collector is always remaining reverse biased when the transistor is working in the active region. Now, there is a base to emitter capacitance, that is a PN diode which is forward biased. Even when the PN diode is forward biased, there is a depletion region in between P and N. So, that capacitance also cannot be ignored in case of high frequency analysis. That is why we have written the CBE. Next, coming to collector to emitter, even though there are no direct junctions, still there are two junctions. That means one base to emit collector is reverse biased, base to emitter is forward biased. So, the net effect of those two junctions will have its own parasitic capacitance. So, that we have shown here as CCE. Now, based on this high frequency modeling, we can rewrite the high frequency model of the amplifier itself using again either RE model or using a hybrid model. So, in this class, let us proceed that way to model this complete amplifier circuitry, and let us perform the mathematical analysis at the input side as well as the output side for obtaining our cutoff frequency at the high frequency range. So let us proceed. So here I have given a brief explanation. CWI is input wiring capacitance, CWO is output wiring capacitance, CBE is transition capacitance, CCE is parasitic capacitance, CBC is feedback capacitance. We have distinct names here. CBE is transition capacitance. In fact, when the diode is forward biased, the capacitance that is occurring across the depletion region, that is called transition capacitance. When the diode is reverse biased, the capacitance that is occurring across that junction is called as junction capacitance. These are typical technical terms. So here CBE is the transition capacitance. CCE is mentioned as parasitic capacitance because it is comprising of the two counterparts, CBE as well as CBC. Now CBC here is called as feedback capacitance. It can also be called as junction capacitance in terms of the diode there because it is reverse biased. But here we have called it as feedback capacitance because output can be fed back to input. That means from the collector, the signal can be coming back to the base. We had done the Miller effect capacitance model by considering the feedback capacitance only. That is CBC, here it is called as feedback capacitance. Now there are two chances. One is, if the input signal is of a very high frequency, that itself can be directly coupled to the collector also without actually being amplified because the capacitor is passing it from base to collector. That is also possible. Another bigger thing possible is the signal which is going into the transistor's base, and when it is getting amplified and it is available at the collector, the amplified signal can come back to the base. When the amplified signal come back to the base, then the collector and the base are actually working in 180 degree out of phase. You already know that the common emitter model is going to produce 180 degree phase shift between input and output. So the amplified output, when it is fed back to the base with 180 degree phase shift, what happens is at the input itself the signal gets cancelled to some extent, because you can visualize one signal having input phase. Let me annotate it and let me try to explain it in a better way. Let us say the input signal is like this and the output signal is now amplified, and let us say output signal is like this. Input signal is very less value, output signal is a larger value, and now this is at the base and this is at the collector. Now because of this CBC, because of the capacitance between base and collector, the amplified output can come back to the base. Now when the amplified output comes back to the base, you can see the net effect here. The input signal and the output signal are out of phase, completely 180 degree out of phase. So the output signal is of larger amplitude, it will try to cancel out the input signal itself. This is going to be a great loss because the amplifier will not get the input signal at all properly. Input signal's amplitude itself gets reduced drastically because of this feedback capacitance. Now you can understand why this high frequency analysis is important. And even when in the RE model and in the hybrid model, we did not consider the capacitance between base and collector, now at the high frequency range, we have to consider that, because in our communication applications, initially we might have started with the kilohertz range. When AM radio came into usage, somewhere at the time of Marconi or Armstrong or Hertz, there is a radio called ham radio, Hertz, Armstrong, Marconi. It was named after these three great scientists. Actually, ham radio was not invented by them, but the ham radio methodology was named after these three scientists. Now that particular radio is also called as citizens band broadcasting radio, where anybody can have a radio equipment at home and you can actually become a ham radio member even now also if you are interested in having such hobby, and you can have communication with another ham radio member. That means at your home you can have this ham radio transceiver. In fact, when a tsunami occurred at the coastal side of India, when all the other communication methodologies had failed, it was the ham radio members who came for a great help. Because when all the radio networks were failed, all other radio networks required a government's establishment or the communication setup. All of them had been devastated. But ham radio is a particular technology where you can use a transceiver at home itself. And that is how you can communicate with the nearest other ham radio member. So that way, when this ham radio was working, they could communicate with each other, and that somehow the people who were affected by the tsunami were helped by means of this particular communication method. So that ham radio was using a range of kilohertz and megahertz, because that was the initial days of radio communication. Later on, we have frequency modulation, AM and FM, that is analog modulation. But present day, now we have digital modulation. We have ASK, FSK, PSK, QAM. We have many such advanced digital modulation methodologies. And now we are using, along with kilohertz and megahertz, we are using gigahertz and terahertz. So that way, when our present communication applications are using the range of terahertz, 10 power 12 hertz. In such a case, when our amplifiers are working, the amplifier's feedback capacitance is going to affect a lot for the terahertz applications. So that way you can understand now, when that base to collector capacitance was not modeled properly, what would have gone wrong in our frequency analysis. That is why the frequency analysis is performed now in the high frequency range, and it is applicable both to BJT or FET or MOSFET or any such active device which is being utilized as an amplifier. Okay, I hope you understood this. Now let me stop annotating and let me proceed. So now, input capacitance CI, let us visualize the input capacitance at this particular circuitry. Let us model the whole thing as CI, and at the output let us model the whole thing as CO. Capacitance at the input, capacitance at the output. Obviously later on we can write it as a high frequency model for the amplifier. So here now, CI is CWI plus CBE plus CMI. Input capacitance is the input wiring capacitance plus the capacitance between base and emitter plus the Miller capacitance of this CBC. The CMI is the input counterpart of this feedback capacitance. Similarly, at the output we have CWO, output wiring capacitance, then CCE, collector to emitter capacitance, and again the Miller's output capacitance, CMO, the output counterpart of the same capacitance CBC or the feedback capacitance. We already know that by means of the Miller's model, we can have two distinct capacitors at the input as well as the output side, that is CMI and CMO. Now using these, we can write the AC equivalent model. Now you can see the AC equivalent model. We have the signal source, then we have the source resistance in series. Then for this voltage divider bias network, at the input we have R1 parallel with R2. Then for the transistor itself, we have this beta into Re. Now for the high frequency, we are adding this CI, input capacitance, which is nothing but CWI plus CBE plus CMI. Let me underline this, because you will have to remember this later on when we solve the exercise. Similarly, at the output we have beta into IB, then we have small r naught, that is part of the transistor itself. In addition, for the high frequency, we have the C naught now, that C naught is nothing but CWO plus CCE plus CMO. Later on, at the output, we have this capital RC, which is the physical resistance in the collector. Later on, we have this RL, or the load resistance. So, I have been telling you that you will have to again revise the first module in order to understand the third module, because all these modules are highly interrelated. If you have not revised the first module and if you have not understood the AC model, then it will be very difficult for you to understand this high frequency model also. When I was correcting the test papers, I have seen that many students have simply written something, somebody has made some error, that same error is continued by so many other students also without actually understanding what they are writing. For example, for one particular exercise in the first test, the answer is 1.41 milliampere. Whoever solved that exercise and passed it on to his or her classmates, that decimal point must have been left out there. So many students have written 141 milliamperes instead of 1.41 milliamperes. I have cut half marks for that particular error. It simply means that those students have not actually worked out that exercise, they have simply copied the same answers everywhere. Even in the AC modeling also, they have simply written some model. But please understand, the answer scripts, whether it is in the test paper or it in the final exam, is evaluated by a professor. Please understand that. Please respect your teachers. Don't underestimate the teaching abilities of your professors or the evaluation abilities of your professors. It is a technical evaluation. You are right now pursuing a professional degree. Please understand that you are going to get a valuable degree, and lifelong that degree is your asset. You will have to be proud that you are going to become an electronics and communication engineer. Now, don't go for such smaller shortcuts. If you go for shortcuts, in future, what will you remember? Now itself, if you don't understand the basics and if you don't try to solve these exercises on your own, how will you understand the third year and final year courses? In fact, in the second year of EC, we have a lot of basic courses. Based on this only, we have advanced courses. Now, if you don't understand the AC model of a transistor, when you come to third year, how will you understand the AC model of a MOSFET? So, my dear students, please be serious in your studies. Please work out all these exercises on your own. Don't simply copy somebody who has done it. I know that you students have a very good unity when you want to share things together. But that what happens there is, if the shared thing is having an error, the same error gets duplicated everywhere in your answer script also. And naturally, things will become public there. Things become public, and I will be knowing in my student class of the students how many are really working out, how many are simply copying. I will be knowing. Now, my question is, don't you care for an opinion of your teacher? You should care for the opinion of a teacher. You should care for the opinion of a parent also. You should really think about how your parents are thinking about you. You should also think about how your teachers are thinking about you. Because in future, when you get employed in a job, you should also think about how your employer is going to think about you. As I've been mentioning, you are into a professional degree. It is not a normal degree. Anyway, let me stop my sermon or advice. You may already be murmuring there, or you may be already be cursing me now, right? I hope so. There are 31 students, so some of you may be already blaming me that instead of teaching, why is he advising? But the question is, if I don't advise you, who else will advise you? That is also a question. If I don't give you professional tips or suggestions, who else will give you? It is the teacher's duty to mold the students, right? It is the way in which we handle you people, the way you will grow up. Because you are all still young and you are all still adolescents. It is the job of we adults to mold you. That is why at times in my theory class, I will have such sermons or advices or suggestions in whichever way you take it. Anyway, fine. Let me stop that advice. Let me come back now. I just wanted to share my observations whenever I correct your test papers. And sometimes I feel upset when I see that in spite of me doing honest teaching, why some of my students are dishonest. That is when I also become upset. But it is up to you. Ultimately, it is your life. It is up to you to correct yourself or up to you to remain that way also. After all, I will be in touch with you maybe in this year, maybe next year, maybe for 3 years. You will be in touch with yourself for lifelong. So you should take yourself seriously. If at all you take my advice seriously, you will take yourself seriously. Otherwise, it is up to you. My job is that I am a talking parrot and I keep on talking. Okay, let me stop all this useless talk. Let me start the useful talk, so to say. I don't know which one is useless or which one is useful. It is again up to you to decide. Let me come back to the AC equivalent model, where again I will go through this once again so that later on we will have to solve these exercises. Now, Vs and Rs is already known. R1 parallel with R2 is already known. Beta Re is already known. Beta IB is already known. Small R0 is already known. RC is already known. RL is already known. The only two different things in this particular model is CI and CO. And please remember, CI is CWI plus CBE plus C Miller at the input. And CO is CWO plus CCE plus C Miller at the output. And you will have to recall again. CMI is what? CMO is what? Again, I am going to show that exercise later on. It is related with the voltage gain. So using this AC equivalent model, let us proceed further. Now let us consider the input side. Considering the input side, FHI means high frequency cutoff at the input is 1 over 2 pi into RTHI into CI. 2 pi. You already know the standard formula. F equals 1 over 2 pi RC, right? FH equals 1 over 2 pi RC. So that what is that RTHI? RTH is the total Thevenin's equivalent resistance. That is RS parallel with R1, parallel with R2, parallel with beta into RE. I hope you already studied the Thevenin's theorem in the course called network analysis. So you will be knowing about it. It is simply an equivalent resistance at the input. And then CI, input capacitance is what? CWI plus CBE plus 1 minus AV into CBC. Now we have the feedback capacitance CBC, that is modeled at the input multiplied by 1 minus AV. Similarly, at the output we will have 1 minus 1 by AV. We are not ignoring that 1 here as of now. Why? For BJT we can ignore. For JFET we will not be able to ignore. That is why let us retain that 1 minus AV also as it is. Or later on also let us retain that 1 minus 1 by AV also as it is. So this is considering the input side. Let us move on to the output side now. At the output side, you can see that FHO is 1 over 2 pi RTHO into CO, Thevenin's equivalent resistance at the output side. That RTHO is nothing but RC parallel with RL parallel with small r0. Please recall the model which I have been showing you few minutes before. And C0 equals CWO plus CCE plus 1 minus 1 by AV into CBC. This is the Miller's counterpart, Miller capacitance at the output. So remember these two. How do we model FHI and FHO? Later on we have to find out which one is a dominant capacitance, just like we did that in case of low frequency analysis, where we used to consider or calculate FLS, then FLE and then FLC. We used to find out 3 frequencies. Whichever was the highest frequency, that we used to consider as the dominant capacitance. Now in this case what we do is, in this case as we are discussing the high frequency analysis, what we do is we will compute this FHI and FHO, and whichever is actually the least frequency, that capacitance is considered as dominant. Why? Because we are moving from a midband gain to the high frequency gain where we are going below minus 3 dB from the maximum gain, and that is where we mark that particular point FH. So naturally, whichever is the least frequency, that capacitance is going to be the dominant capacitance, because the higher frequency is anyhow going to come down below that 3 dB, and we are not interested in the further frequencies. Anyhow, the gain is going to be lesser there. Okay. Now, later on we will have the exercises based on this FHI and FHO. Now, let us slightly discuss this HFE variation, because we will have to have a slightly different hybrid model now. So, let me discuss that. Considering the HFE variation, this HFE need not be constant throughout. That is why beta and HFE are considered slightly different. Again, I had discussed about beta DC and beta AC. DC current gain, AC current gain. That AC current gain is only with reference to the small signal analysis at the Q point. Beta DC is a common fixed value for a given transistor. It's a DC current gain, capital IC by capital IB. Now, HFE is what? Hybrid forward emitter, right? It is a forward current gain for the common emitter circuitry. This is going to be computed by the manufacturer himself. Now, the value of beta or HFE, you should mention it as value of beta AC here. Even though I have not explicitly mentioned it here, you should understand it. So, the value of beta or HFE will reduce at higher frequencies with the 6 dB per octave slope that we have already seen there, right? 6 dB per octave plus slope. Now, I have put a small at symbol there. I will show you here. I have written it as a footnote or a side note here. I cannot say footnote, it's a side note. Because I was writing the handwritten notes, I found a space somewhere here and simply I have written it. You may have to read it with the tilting your head now. HFE is HFE mid divided by 1 plus J into F by F beta. Okay, HFE mid, the midband gain, or at the midband of the frequency response, the gain is constant. So naturally, HFE also is constant. Now, based on that, we can model the complete HFE as 1 plus J into F by F beta. So that way, hence F beta can be determined by using the hybrid pi model. Let me admit the student who is waiting in the lobby. Okay. Now, the S beta can be determined by utilizing the hybrid pi model. What is this F beta? The frequency which is corresponding to beta itself. For that, we have a hybrid pi model, just like we had a hybrid T model. No, sorry, hybrid pi model only. In RE model, I had discussed about the Ebers-Moll model or the T model. We had a normal pi model only. Actually, till now, we had discussed in this module only, in between the low frequency analysis before the Miller capacitance, we had discussed the hybrid model only. Now, let us have a hybrid pi model here, where you can see at the base there is this small RB and there is this beta into RE. That small RB we had ignored till now, thinking that the base resistance can always be ignored. But here in the high frequency model, let us add that also along with beta into RE. Then we have this CBE, which you are already familiar. Then beta IB and R0, you are already familiar. CBC also you are already familiar. But let us add one more thing called RBC. That is the resistance between base and collector. In general, this will be a very high resistance. So because it is a very high resistance, till now we did not add it. We simply ignored it. Because when compared to beta RE and R0, that RBC need not be there. But let us add that also now. Now this is going to become a hybrid pi model, which is a more accurate model when compared to the earlier models. But this model was not necessary in case of our low frequency analysis, because as I told you that small rb can be completely ignored because it is very less value, and that small rbc also can be completely ignored because it is a very high value. But let us add it now because we are dealing with the high frequency analysis. So using this, we can find out one more expression called f beta. Along with fhi and fho, we can have one more frequency called f beta. So here CCE is ignored as it is much smaller when compared to the other two. Collector to emitter capacitance is actually a composite capacitance of collector to base capacitance and base to emitter capacitance. So it is of much smaller value. It can be ignored when it is compared to CBE and CBC. So using this hybrid pi model, we can write an expression for f beta. That is, you already know that f is 1 over 2 pi rc. 1 over 2 pi into beta into re, where this beta into re is there, and CBE plus CBC, CBE plus CBC, these two are considered. And or f beta can be written as 1 over HFE mid, using the expression which I had written on the side, 1 over HFE mid into 1 over 2 pi into RE into CBE plus CBC. That beta we will take it this side. This beta, instead of beta, we will write it as HFE mid itself, because HFE mid is given by the manufacturer. So that way, we can separate this beta, we can write it as HFE mid, and we can write it as 1 over 2 pi into RE into CBE plus CBC. So if you know this small RE, if you know CBE, if you know CBC, you can find out f beta. Let me admit the student. So even though we have written the hybrid pi model, that small rb and capital R, small rbc, we did not consider here at all. Why? Because we are mostly interested in these values, these three values, beta into re, cbe, cbc. Other two values are not actually going to be so much dominant in the computation. So now we have three equations, FHI, FHO and F beta. For the computation of F beta, only the feedback loop is considered. See, this is the feedback loop. Let me annotate. This is going to be the feedback loop, right? Output signal is coming back to input by means of the CBC. I had already shown you earlier that the 180 degree out of phase two signals are going to cancel out the input signal itself. So that way, this is the feedback loop now. In the feedback loop, this small RBC need not be considered because it is very high value, and CBC and CBE and beta RE are considered. RB is not considered because that is also not coming under the feedback loop. It is part of the input side fully. So that is how only beta into RE, CBE and CBC are considered. So in this way, for the computation of F beta, only the feedback loop is considered. Now we have one more important concept called GBP, gain bandwidth product. Let me drink a little water. Gain bandwidth product. You can see this particular graph here. Let me discuss the upper graph first. Now let us say we have a 40 dB gain for a given amplifier circuit. When we have a 40 dB gain for a given amplifier circuit, we will measure its bandwidth by coming down to here 37 dB and again here 37 dB. 40 minus 3 is 37 dB. Wherever is that particular 37 dB, let me annotate that. Wherever this particular 37 dB, there we mark 2 points and then we write it as FL1 and FH1, and this is what we consider as bandwidth now, bandwidth 1. That is FH1 minus FL1. Now you can see gain is higher but bandwidth is lower. Okay. Now let us come back to one more amplifier. Let us have the reduced gain of an amplifier. Let us consider the gain as 20 dB now for a given amplifier. Now 20 minus 3 is 17 dB. We will have a frequency response of the second amplifier also, and there it is at 17 dB we will mark FL2 and FH2, and then we will measure this bandwidth. Bandwidth 2 is FH2 minus FL2. So now you can see bandwidth 2 is larger than bandwidth 1. Okay, but the gain 1 is larger than gain 2. That also you can see. 40 dB is larger than 20 dB, but bandwidth 2 is larger than bandwidth 1. So what does it mean? It means that when the gain is reduced, bandwidth is increased. Why? Because we measure the bandwidth with respect to the 3 dB cutoff, and actually the curve is going to become more flatter when the gain is reduced, right? When the amplifier's gain is reduced, the curve is going to be nearer to the x-axis, and gradually it is going to widen up. When the frequency response is going to widen up, automatically the bandwidth will be larger when the gain is lesser. Similarly, bandwidth will be lesser when the gain is larger. So, we have something called gain bandwidth product. Gain into bandwidth. Okay, that we generally call it as GBP, gain bandwidth product. For a given amplifier circuit, GBP is constant. In the sense, let us say I have 40 dB and let us say I have 20 megahertz bandwidth 1. 40 dB into 20 megahertz. So how much it becomes? 40 into 20. Nakalient. 40 into 20. It is the product which is 800 now. I am giving an example of bandwidth 1 as 20 megahertz. So 20 megahertz into 40 dB is 800. This is now GBP. So we can say if this is now 20 megahertz, I'm just giving an example. Okay, I'm just giving an example. Okay, so 40 into 20 is 800 is GBP. Naturally, this 800 is a constant value to this particular amplifier. Now you should tell me, what is bandwidth 2 now? Can some of you immediately tell me? You already know that I am bad in mental calculations. I always require paper and pen. But you belong to new generation. You are quick in mental calculations. So can you tell me what is bandwidth 2? GBP is fixed now. 800 is fixed. So what is bandwidth 2? Anybody? 1600. Is it so? Rutesh has given the answer 1600. No. See, it is gain bandwidth product is 800. That is fixed. Now at the numerator you have gain and bandwidth. Here you have gain. So it is 800 by 20. So that is 40 megahertz. It is now 40 megahertz. Okay. So you see 40 dB into 20 megahertz is 800. 20 dB into 40 megahertz is 800. You can see when the gain was 40 dB, bandwidth was 20 megahertz. When the gain became 20 dB, the bandwidth became 40 megahertz. So for a given amplifier, gain bandwidth product is constant. So in the analog circuit designs, if you design an amplifier which is going to have a larger GBP, then your design is really a very good design, because always require a larger GBP. What we want is, we want the larger gain also, we want the larger bandwidth also. but both are not possible that way. Once, if you want higher gain, bandwidth will reduce. If you want higher bandwidth, gain will reduce. You will have to make a compromise. That is when we choose such amplifier for the given applications. But in general, what we want? In general, we want the most out of any technology. If at all we have an amplifier which is going to have a GBP of, instead of 800 now, let us say GBP of 1000, 1200, 1400, maybe 2000, maybe 20,000, maybe 1 lakh. Let us say the GBP is 1 lakh. Then it means gain bandwidth product is much larger. If it is much larger, naturally the amplifier is more suitable to many applications. That is the idea. Any particular amplifier which is going to have a GBP larger, then it means that it is suitable to many communication applications. That is the challenge here. So, again you may think, how is it possible to have a GBP of 1 lakh for a given amplifier circuitry? It is possible provided you model the complete amplifier in terms of all the frequencies, low frequency, mid frequency, high frequency, and you plot this frequency response curve, and somehow you work out with the same biasing methodology or with the better transistors model about how to have a larger gain also. So that is the skill of an engineer, nothing else. Skill and knowledge together are going to be useful in the electronic designs. Initially you should have a theoretical knowledge, then you should have a practical skill. Together they are going to yield very good designs. In fact, we have one triangle or set of 3 circles in our character model, that is called knowledge, skill and attitude. If you visualize a triangle, equilateral triangle, then one side is knowledge, one side is skill, one side is attitude. The baseline you should indicate as attitude. You should have a learning attitude. Based on your attitude only, you will gain knowledge or you will develop skills. Knowledge and skill both are ultimately dependent on the attitude. Okay, that is the philosophical side. Now coming back to technical side, if you can use your knowledge and skill together for designing an amplifier which is having a much larger GBP, then that is a very good design, because that is applicable to all other communication products. So that way we have a term called GBP. Now you can see FH1 minus FL1 is less than FH2 minus FL2. That means bandwidth 1 is less than bandwidth 2. And you can also see FL is much lesser than FH. This lower frequency is always in few hertz, whereas few kilohertz. Whereas FH will be always in few megahertz or gigahertz or terahertz. So in such a case, in most of the cases, we can ignore this FL1, FL2 itself, because they are at the only a lower frequency range, and you already know that we are plotting this graph using a semilog x-axis. So at times, FL itself can be ignored. Therefore, bandwidth is more when gain is less. GBP is a constant at any level of gain. The unity gain frequency Ft is defined. Unity gain frequency means the frequency at which gain becomes unity. Gain becomes 1. You can see here at the high frequency range also gain is coming down. Here it is becoming 0, right? Ft at the point, let me annotate it. At this point here, Ft, the gain has become 0 dB. 0 dB means what? Output is equal to input. So we should find out this Ft. It is also called as transition frequency. T stands for transition, where output is equal to input. Later on, if you increase the frequency, output will be less than input. Why? The curve will go down like this. The curve will go below 0 dB. When the curve goes below 0 dB, that means what? Minus 1 dB, minus 2 dB. That means output is less than input. Amplifier will not work like an amplifier at all beyond Ft. So that Ft or a unity gain frequency is defined as AV mid into FH, the midband gain into FH, where we will simply ignore FL when compared to the higher frequency ranges. Now for transistors, this can be written as Ft equals HFA mid into F beta. Okay, you don't have to worry too much about how we arrive at all these equations. The derivations of these equations are beyond our curriculum. So for transistors, this Ft equals AV mid into FH is completely for a amplifier circuit. Now taking only the transistor into consideration, Ft equals HFA mid into F beta. So Ft is 1 over 2 pi R into CBE plus CBC, because we already have an expression for F beta. You already have this expression, right? We have the expression for F beta, 1 over HF mid into 1 by 2 pi R into CBE plus CBC. That we are going to substitute here. Now here we have Ft equals 1 over 2 pi R into CBE plus CBC, because this HF mid gets cancelled with the one at the denominator. Now this is going to be the transition frequency, or this is called UGB, unity gain bandwidth, because the gain is unity there at that time. Output equals input at that time. So this is called UGB, unity gain bandwidth is a figure of merit for the amplifier. That means that is the maximum frequency at which you will be able to use the amplifier, beyond which it will not work like an amplifier at all. So with this discussion,